Okay, so in the last few lectures we talked about the scalar gravity, the spin zero gravity, which we also call the theory of dilaton, and we worked out some of the predictions of this theory, like for instance the motion of the particles in the background field, the gravitational redshift, and the emission of waves, dilaton waves. So one thing that we saw was that the predictions of this theory are incompatible with observation. For instance, it predicts zero bending for light, which is, now we know it's not true. We have a non-zero bending of light by the sun, for instance. And also, its prediction for the emission of gravitational waves, we saw in the previous lecture that it leads to some rate of change of the radius of a binary system, right? If I have a binary system, it emits these dilaton waves and it loses energy, and because of that the radius changes, and also the orbital frequency of the binary system changes. That is also that is also ruled out by observation, meaning that there are some binary systems called pulsar binaries, and those the rate of change of the orbital frequency of those pulsar binaries is measured very precisely, and the rate of change does not agree with what we get from dilaton gravity. So we have enough evidence that this is not the correct relativistic theory of gravity for our universe. So we want to go to the next option in our list, which is having graviton to be a spin 2, massless spin 2 field. So the goal today would be to construct this theory of a massless spin 2 that has the right non-relativistic limit, so that it gives the Newtonian gravity, and then we work out its predictions at the linear length. Okay, so we want to consider a particle which has a mass equal to 0, and we said that particles with mass equal to 0, when we study the representations of Poincare, they are classified by the helicity, but this particle has a helicity plus minus 2. Remember, helicity, to define it, what we do is that we use this method of induced representations. We go to some particular frame and say a frame in which the particle, the massless particle, has a momentum p mu given by, say, 1 electron volt, 1, 1 and 0, 0. So it's a particle that moves along x direction. And then we look for the representations of the subgroup of the Lorentz transformations that preserve this momentum. So now you can easily see that a rotation in the YZ direction would preserve this. There are some other generators, the combinational generators that preserve this, but those are discarded or assumed to be trivial based on some other considerations, based on the requirement that we want finite representation. So we end up with SO2. This is O2, the subgroup that preserves or preferred momentum is called the little group, and we identify the representation, massless representations by the representations of this SO2, which is just a real number. But then we use the global structure of the Lorentz group, which tells us that the 4-pi rotation has to be identity to conclude that or helicities has to be, or 2 helicity has to be an integer. And then, for instance, we can use parity to conclude that we need plus and minus helicities, because parity switches the sign. So at the end of the day, we have 2 helicities for any massless particle with non-zero spin. 2 photons, 2 gravitons, and so on. If it is massless, then it can have only one area. Okay, now this spin 2 particle with helicity 2, it has to be described by a field with 2 Lorentz indices. You have to put this creation and annihilation operators for the massless spin 2 particles in a field, because now we want to construct a field theory. So we want to put this part 2 degrees of freedom inside this field, but this field has many more independent components than the number of gravitons, right? So if you count them in 4 dimensions, the number of independent components of this h mu nu is 10. So in general, it is d times d plus 1 over 2, which is going to be equal to 10 in 4 dimensions. So we have 10 independent components in h mu nu, but we only want to describe 2 helicities of graviton. So there is a redundancy in this description, and somehow we should get rid of that. This is reminiscent of the case of electromagnetism. So if you remember the case of electromagnetism, there we also have 2 helicities of photon. So helicities can be plus or minus, so we have 2 polarization for photon. But we want to describe it by a vector field, a mu which has 4 components in 4D. Again, you see there is some redundancy in this description, and the way this redundancy is eliminated in Maxwell theory, when it is formulated in terms of A mu, is that there is a gauge symmetry. There is a U1 gauge symmetry that identifies A mu plus A mu, identifies A mu with A mu plus d mu of alpha for any function alpha, an arbitrary function. At the level of the, so therefore we construct an action for A mu that is invariant under this gauge symmetry. At the level of equations of motion, the implication of this symmetry is that if we look at the Maxwell equation, d mu f mu nu equals j mu, the left-hand side, which is the homogeneous part of the equation, is identical concept. This is to say that d mu f mu nu is equal to 0 as an identity. It doesn't matter what a mu field I'm using. It's not an equation of motion. It's just a consequence of the anti-symmetry of f mu nu. That implies that if this equation is to be valid, it has to be valid. It has this j nu that sits on the right-hand side has to be conserved on shell. So therefore we can couple a mu to matter field. So imagine we want to write some action for a mu on matter field. So there is a part which contains a. This looks a bit weird. Let me write it like so. There is a. We want to write the action as the part that contains a. Plus a part which comes from the matter field, which doesn't know about A. And in order to be able to couple a mu to some matter fields, the condition is that this matter field has to have a symmetry and an associated conserved current. And that conserved current can sit on the right-hand side of the Maxwell equation. So now this is similar situation is going to happen in the description of the massless spin 2 field. We have a redundant description, and to get rid of this redundancy, we need to impose a gauge symmetry. Now the redundancy is larger, right, from 10 to 2 instead of 4 to 2. And also the gauge symmetry is larger. Now the gauge parameter, now I call it xc, it's a 4 vector. There are 4 arbitrary functions. And we construct a theory that is invariant under this larger gauge symmetry. So now again, at the level of equations of motion, this implies that the equation of motion that we write for h mu nu is going to be identically conserved. So how would this equation look like? First of all, this equation of motion that we write for h mu nu is going to, we expect to have a second order differential equation, which is Lorentz invariant, because, for instance, we wanted to have the right non-relativistic limit. So we wanted to go to the Poisson equation. Moreover, for single particle, we wanted to be reduced to the Klein-Gordon equation for that particle, or the on-shell condition for that single photon.
So we're going to make a theory which is invariant in this gauge transformation, right?
Yes.
So before doing that, is there any easy way to see that that there is an often quoted statement that gravity does not have any global symmetry? So why is that?
Oh, that is way beyond the scope of this course.
Okay.
So
there's no easy way to see that.
Actually, when you learn about black holes, you can ask Paolo about that. It's actually easy to understand when there are black holes. When you learn about black holes, but now no way I can do it. At this level, I don't have any general arguments against global symmetry. It's supposed to be an issue with quantum gravity. At the moment we are doing classical gravity.
So there is no issue in classical gravity?
No. Although here I talk about quantum mechanics and how we need this representation when we can talk about combining quantum field theory and gravity. Anyway, so we want to construct the equation of motion for h mu nu as a second order differential equation that is Lorentz invariant. Of course, there is also no mass term in this equation because there's no potential. So let me just write the most general Lorentz invariant equation that we can have. also use the symmetry of, this is a symmetric field. I never said it, but then we can have B times d mu of H, where H is the trace of H mu. So H is H alpha, which is eta alpha beta times H alpha beta. So what else I can write? I can write plus d eta mu d times, no, maybe d is not a good, e times box H plus f times d alpha d beta H alpha beta. And then I should have a source. So you can see that here you can verify that I have written all possible two derivative terms that I could write. Oh, by the way, the equation has also two indices. Again, because I'm writing an equation for this spin 2 field. So I've written the most general object which has two indices, the tensor equation, and has two derivatives acting per field, and is linear in H. There has to be a source on the right hand side, and that source has to be conserved analogously to this, to the case of Maxwell theory. So we want to construct a theory which has the property that it is invariant under this symmetry, this transformation, gauge transformation. This is one.
So right now you are interpreting that this field is just a tensor field in space-time.
Yes.
So you're not saying that it is a correction to the metric or something?
No. It's, at the moment, this is just a field theory on Minkowski's.
Okay.
And the equation has to be identically conserved. So if I write this differential operator, I just use this shorthand for it as epsilon mu nu alpha beta acting on H alpha beta. In fact, let me do it. Let me do this definition here. So this operator is a linear differential operator called epsilon mu nu alpha beta, and it has the property that it is identically conserved, meaning that this is equal to 0.
Is it total antisymmetric tensor or just another symbol?
Sorry?
Is it the totally antisymmetric symbol or another symbol?
Oh, no, it has nothing to do with that. It's just this operator that I have here. Okay. It is actually symmetry. No.
So in mu and nu it has to be
symmetry under the exchange of mu and nu and under the exchange of alpha and beta. So this is the first property that I want this equation to satisfy. This is the second property. The second property ensures that what I put on the right hand side of the equation has to be conserved. And the option that we have is obvious, is the T mu nu, the energy momentum tensor with some unknown coefficient. And this T mu nu, at the moment we are working with the linearized theory, so this is supposed to be T mu nu 0 or matter. But later I might drop this in superscript n. But this should be understood, since it is a linearized theory, it should be understood as the part that comes from the matter action, not from the H mu nu part of the action. So what else? Now, I want to choose the normalization of h mu nu so that this coupling between h mu nu and the energy momentum tensor is of the following form. So S interaction, I want to write it in this one, h mu nu times t mu nu. And so far it's not restricted. I can always choose the normalization of h mu nu so that this is the coupling between h mu nu and mass. What it changes is that not the kinetic term for h mu nu that I'm gonna write. That will have some normalization factor. Remember, for instance, in the case of a scalar gravity, what we wrote was phi times t. And then the kinetic term for phi had some non-trivial coefficient behind. There was 1 over 8 pi g in front of the kinetic term. So similarly here, I fixed for later convenience, I fixed this coupling between h mu nu and t mu nu.
In the scalar case, we had a reason that we want the theory to go to Newtonian results in the non-relativistic limit, but what is the reason here?
We still want that. Actually, this is the third requirement. Newtonian limit. We want to recover the Newtonian limit correctly from this theory. That doesn't say anything about this particular interaction, because this is just you can think of this equation as just choosing a normalization for h mu nu. So however you wanted to couple h mu nu to t mu nu, you can absorb that coefficient inside that. Okay. I still have this unknown parameter here. That is the one that will be fixed by the correct Newtonian limit. Okay, so now our task would be to fix this unknown coefficient. By trying to satisfy those requirements. So how do we do this? We can do the following. First of all, I use this this invariance. So the theory is supposed to be invariant under this transformation. I use it to so let me. I use this invariance to make h mu nu simpler. What do I mean by this? I want to choose these functions xc so that the mu of h mu nu is equal to 0. Or in other words, maybe let me write in a different. So I want to define a new h tilde mu nu, which is h mu nu plus d mu x nu plus d nu x mu, such that the mu of h tilde mu nu is equal to 0. So this gives me, these are 4 equations, right? Because there's an index, 3 indexes. These are 4 equations which I can solve for these 4 variables, 4 functions, xi, mu. So I can choose this xi mu such that this condition is satisfied. Once it is satisfied, then we still have some additional freedom, because if you do an extra transformation, what it does is that let us act by this d mu on this object. Or let us do a second transformation. So h tilde mu nu, let's write it as h double tilde mu nu. Let's write it as h tilde mu nu plus d mu xi tilde mu plus d mu xi tilde mu. So let's do a second diffeomorphism. And then ask that, ask what is d mu of this new field. So it will be d mu of h tilde mu nu, which is 0, plus d mu acting on this two parts. So this is going to be box x tilde mu plus d mu xi tilde mu. Now if I want this new h mu nu double tilde to be also satisfy this condition, that puts a constraint on this new transformation.
It didn't the sourceless Maxwell equation, like the sourceless Maxwell equation for the potential. Okay.
Is this like a sourceless Maxwell equation? Well, I guess the sign would be the opposite.
Yeah. The only difference is the sign.
The sign, the indices don't agree.
The indices don't agree. You are right. Thank you. Okay, so now from now on I want to drop all of the tildes, because then it becomes too messy. So in the future we might do this frequently, that we do a transformation, we go to a new, we consider well, this is called going to a different gauge, right? When we are doing a gauge transformation, this is a gauge transformation. So we perform a gauge transformation, we get the field. Now field in this, after that transformation, is called the field in the new gauge. So this h tilde is a field in this new gauge. In this gauge, h tilde mu nu is divergenceless, but there are a subset of gauge transformations that preserve that condition. So we want to go to that gauge with this condition is satisfied, and then forget about this tilde. So from now on, or at least for this part of the discussion, h mu nu is divergenceless. So we know that we can do this, and we know that this condition doesn't totally fix gauge transformations. There are some residual gauge transformations that keep this condition. Okay, now if I do that, then this equation simplifies. So now the equation will look like box h mu nu plus b d mu d nu h plus e eta mu nu box h is equal to c times t mu nu. Okay, so now we want to impose two requirements. One is that under this residual gauge transformation, this equation is invariant. Remember, we wanted the equation to be invariant under all gauge transformations, so they should be invariant under the residual ones that preserve the gauge condition. So what it means is that box d mu xi mu plus d mu xi mu plus b twice b times d mu d alpha x alpha plus d eta mu nu, again twice e eta mu nu times box d alpha x alpha has to be 0. So this is the change of the left hand side on the gauge transformation. We remember that gauge transformations, this residual gauge transformation should satisfy this extra condition. Otherwise, if they don't satisfy, we are going out of this gauge, which means that then we cannot forget about the terms that I dropped. So we have to only impose the residual one. And this condition implies that this residual gauge transformation, in particular, it implies that if I act by d nu on this equation, right, act by d nu on this equation, you get twice box d mu xi mu is equal to 0. So box d mu xi mu has to be 0, which means that this term is equal to 0. What else? It also tells us that, so we can also replace, for instance, these terms. Again, using this equation, we can write them as minus d mu minus twice d mu d nu d alpha x alpha plus 2b d mu d alpha x alpha equals to 0, which tells us that b has to be 1. So this is the first condition, the gauge invariance of the equation. Then I want it to be divergenceless. I want this equation to be divergenceless. So I act by d mu on it. And I want it to be divergenceless as an identity. So if I act by d mu on this equation, I get box d mu h mu nu. Now we know that b is 1. So I get box d mu of h plus e d mu box h. And this has to be 0. Identical is 0. This first term is 0 because of our gauge condition. So in order for the second two terms to cancel, I have to have e equals minus 1. So I fixed b and e. Now we can go to the original equation with these choices of e and b and require the original equation to be invariant under the general gauge transformation. And that would fix also a and f for us. And C will be fixed later. So eventually we get the equation which will look like, okay, I won't write the equation. I just write the values for A, B, E and F. So A has to be minus 1, B has to be 1, E minus 1, and F as 1. We still need to determine C. Any questions so far?
do I can reach this equation?
The one, which one? This one at the top?
The one at the bottom.
This one? So what I did from here to here was that I performed a gauge transformation on the left hand side. So here I have written only the change of the left hand side. And we want the change to vanish, because we want the equation to be invariant on the gauge transformation. So the analogous case would be that when we write Maxwell equation, d mu f mu nu is invariant on the U1 transformation. So the equation is invariant on the. So that's how I got from here to here. However, we should remember that only a subset of gauge transformations are allowed, because I have dropped some of the terms from the original full equation, assuming some condition. So only the gauge transformation that preserve these conditions are allowed. So that is I impose that conditions on xi, which keep this term, and then simplify the rest. And then I require that to be 0.
How did you get the value of A and F?
Oh, well, you just plug in B and E as derived from there, and then you apply a general gauge transformation in this equation, and then make the same requirement. I want this equation to be invariant on the general gauge transformation. Now, when I look at the full equation, I don't need to impose any condition on xi. For any xi, it has to be unchanged. And that fixes the relation between A and B. That gives you two conditions that allow us to fix A and F in terms of B and T. Okay. Other question? Now, in order to fix C, we have to, of course, that requires some physical input. That C has to be dimension full, so there should be some constant of nature appearing here. Obviously, the G Newton has to enter there, and there should be some physical requirement to fix it, which is the Newtonian limit. So to see that, we should first understand how to relate this nu h mu nu phi to the Newtonian gravitational potential in the Newtonian limit.
What is the dimension of H field?
The dimension of the H field is 0, is dimensionless, because T mu nu is dimension 4, before H is dimension -4, so H has to be dimensionless. Okay, so the first task would be to connect H mu nu to the Newtonian potential in the Newtonian limit, and then we can fix C. So the way we do that, again, there are various ways of doing that. Of course, one thing that we can do is similar to this exercise that you all did. Consider scattering of particles with the exchange of massless spin 2. And require that scattering process in the non-relativistic limit that gives you the same scattering cross section as the usual gravitation 1/r² interaction. That would fully fix this coefficient for us. The other alternative way is similar to what they did for scalar gravity, is to look at the motion of point particles in an external field and see how the external field affects the motion of the point particles, and require that and compare that with the effect of the Newtonian potential on the motion of particles. in the non-relativist.
I was asking that because if H has dimension 0, then if we just compare the dimensions of the equation, then we can come to know that C should have dimension 2. So is there any constant in our theory that has dimension 2, or its power can be used to?
The C has to be dimension minus 2.
T has dimension 4.
Yeah.
And the left-hand side has dimension 2.
Yeah. So C has to be dimension minus.
Yeah, sorry, minus 3.
Yeah, and the constant, the natural suspect is G Newton, right? It has dimension minus 2.
So is that G only, or G times some constant factor?
Yeah, that's what we should do. Of course, it has to be proportional to G Newton, but the question is that what is the proportionality constant?
Okay.
And that's what for that we cannot determine just by dimensional analysis. We need to be a bit more quantitative. So we look at the point particle action. This is perhaps the fastest way to fix this constant.
And the other way that you mentioned, using scattering amplitudes, would that be a homework problem?
No.
No. I was thinking that it might be a bit difficult to derive the finite growth for H mu nu.
Yeah, it's not too difficult, but it's not a homework problem. Because remember, you want to do it only in the non-relativistic limits, so things become relatively easy. But you know how to derive the propagator for the Maxwell field, right?
Yeah.
So the denominator is always the same. If you have massless particle, it's just you have 1 over p squared. The numerator is a tensor that whose structure you get it by looking at the equation of motion. By inverting that, of course, we cannot invert these equations. They are singular because of the gauge symmetry. So the way to do it is to do some gauge fixing. And that gauge fixing allows you to invert this tensor structure. But eventually you get some tensor structure to put in the numerator, and then you're basically done.
So in this case, we will have a numerator which is a 4th rank tensor.
Yes, yes.
Okay.
So yeah, the only extra work compared to what you have already done is to find that tensor structure, and it's some algebra.
Only for the propagator in that case.
Yeah.
Okay.
T mu nu, you already know what it is, right? I mean, you just consider some scalar field, you know how to write this.
But what about the vertex?
Direction.
What about the vertex?
Oh, I have written it here.
So you will, okay, H, okay.
So it's nothing beyond what you already know.
Okay.
I have a question.
Or what you are assumed to already know. Yeah.
Actually, why it is necessary to have two polarization for two particles or gravity?
Say it again.
You said that helicity has 3 modes, two modes. Why it is necessary?
Why are there only 2? Well, this was the result from the representation theory of Poincaré. So what we were doing was that we were looking for this irreducible representation. Now we want a massless, irreducible massless representation with a spin 2. We saw that for massless particles, we should look at the representations of SO2, that is called the little group. So that's the rotation along the momentum of the particle. So this has to have the property that this is a natural thing that you would expect, right? It has to be if it's a spin 2 particle, it has to, when you rotate by angle, I don't know, alpha, you have to get a phase which is e to the 2I alpha.
If the graviton would be massive,
Uh-huh.
will it be the same?
No, if it's massive, it will be 5. So that's the difference between massless and massive representations. Instead of talking about representations of SO2, in the massless case, which is this little group, which are rotations along your reference momentum, in the massive case, you go to the rest frame. And in the rest frame, we talk about representations of SO3, because now rotations in the rest frame, all rotations in the rest frame preserve the particle at rest. And then for spin 2, you have spin 2 representation has 5 degrees of freedom. So there is a discontinuity between massive and massless. You cannot obtain massless one by just taking the m to 0 limit of a massive representation.
It's just like the Broca and Maxwell technology.
Yes.
And it is its index will be symmetric only for that it will be coupled with stress tensor. That's the reason?
The reason why I'm using a symmetric tensor is why is that's something that we actually didn't talk much about it. We want to basically, when you want to construct a field theory, you want to package those degrees of freedom that we talked about, like the 2 helicity modes. You want to put it inside the field. Now I want to construct a field that has the minimum amount of freedom that allows me to construct the theory. The symmetry of the indices, you could consider a general field which is not symmetric, but it's enough to consider a symmetric field. Let me say it this way. It cannot be anti-symmetric, because if you wanted to do a rotation along some axis, a particular component of this has to rotate by the angle, by a phase which is, imagine you do a rotation at angle theta. If you say your particle has this helicity 2, so suppose it's moving in the one direction, right? This is, its momentum is given by, I don't know, 1, 1 and 0, 0, right? And you want to do a rotation in the YZ plane, meaning that it's a rotation along the axis of the motion, right? Then the state of the particle under this rotation has to gain a phase which is 2I theta, if you say that the helicity of the particle is 2, right? That's the meaning of having helicity 2, which that means what it basically tells you under SO2 rotations in this YZ plane, how much phase do you gain. So you want to gain a phase which is e to the 2I theta, and then you can ask what kind of field you need, what tensor field you need, so that under rotation, what Lorentz field do you need, so that under rotation, so if you apply lambda mu alpha, lambda mu beta on this field to get the new field, under that particular polarization that you are interested in rotates by this amount, e to the 2I theta. And then from that you see that you need a symmetric rank 2 representation.
Because the antisymmetric will not contribute.
Right. But if you would like to learn more about it, I recommend looking at Weinberg's book. I think the QFT book, I think in chapter 5 he talks about this. how to construct quantum fields for the representations of Poincare. Other questions? So what we want to do is to determine C. And in order to do that, we want to look at we want to relate H to the Newtonian potential. And in order to do that, we want to see how the motion of a particle is affected by background field H mu nu. So you should think about some H mu nu field as a background field on a particle that moves in here, and we want to see how its motion is going to be modified because of H mu nu. Now I have already fixed the coupling of H mu nu to the matter fields. That already tells us how to couple H mu nu to the point particle action, because we know what is T mu nu for a point particle. So in order to reproduce this result, there is a particular term that we need to add to the point particle action. So this was originally we had just the free action. And to this action we need to add the extra term, which is minus 1/2 H mu nu dx mu d sigma dx nu d sigma divided by the same square root.
That's a thing for particle.
Right, this is exactly. So this is what, if I now put the solution for this x in this action and write it in the four-dimensional way by introducing a delta function, I will recover this equation. But now, of course, this is the coupling at the linearized order, right? We are working at linear order in H mu nu. So I'm not keeping track of higher order terms in H mu nu. So we can equally well write this term in a more suggestive way. We can take it inside the square root and write it as minus g mu nu of x times dx mu d sigma dx nu d sigma, where g mu nu of x, this is defined as eta mu nu plus h mu nu of it. But the difference between this expression and that expression, after I plug in this expression for g mu nu and expand, will be higher order in h mu nu, which at the moment we don't care about. And then deriving the equation of motion from this action is easy. We have already done it before. So we get d by d tau of g mu nu dx nu d tau equals 1/2 d mu nu of g alpha beta dx alpha d tau times dx beta d tau. Any question?
There should you write in that? There should you write as no instead of sigma.
Where?
In the second step. Here.
Here?
Yeah.
No. Why? Well, if you agree with that, this is just these two terms are equivalent to up to linear order in HEP-GR.
Oh, okay. Linear order.
Remember that the word line action is reparametrization invariant. It shouldn't matter how I reparameterize it. So whatever you write has to be invariant under that. This is reparametrization invariant. That was reparametrization. Okay, so this is the equation. And then we can take the, as usual, we can take the non-relativistic limit. Of course, we want to linearize in HEP-GR, so it simplifies. Also, we want to work now in a different gauge. I want to work in a gauge in which H0i is equal to 0. Working in that gauge means similar to here. I'm choosing xi mu such that I satisfy that condition. And you see that I have enough freedom to do that because that is 3 conditions. I have 4 free xi. So I impose that condition and I consider the mu equals I component of this equation. So there is no off-diagonal terms in it. This is by the way it's called a metric. There's no off-diagonal terms in this metric because of that condition. So if I look at the I component of this, it will be let us look at the mu equals I component. Then in the left hand side I have d by d tau of gij dxj d tau. This is the left hand side. Cool. And of course, non-relativistic means that time derivatives are, the velocities are small. So here I'm gonna ignore the correction to gij. So this two leading order will be just d squared dx squared dxi d tau squared, and which is equal to d squared xi dt squared, because in the non-relativistic limit the time, proper time and the time that the clock measures are the same. Something that I forgot to mention is that here this tau that appears here should be this should be tau tilde, where tau tilde is defined in terms of the metric g mu and u. So the tau tilde square is minus g mu and u dx mu dx mu. But again, for the purpose of taking this limit, that even that difference doesn't matter, because we are already talking about something which is first order, so difference between tau and tau tilde would introduce a second order correction. So this is for the left hand side, and then in the right hand side, the term that is leading is when I take alpha and beta to be both 0, because I'm talking about the non-relativistic particle. Therefore, when I look at the zeroth component of the 4 velocities, I get something about the 1, while the vector component, the space components are gonna be suppressed. So the right-hand side would be 1/2 the mu of, again we are looking at mu equals I, so 1/2 the I of G00, the I of eta is 0, so I can write just the I of H00 times the zeroth component of the 4 velocity, which is almost 1 in the non-relativistic limit. So that's just that's the right hand side. So here is the equation that we get: d2xi dt squared is equal to 1/2 the I of H00, which tells us that H00 has to be minus twice, has to be identified with minus twice phi Newtonian. Once we make this identification, then we can determine C relatively easily. So now we want to take the non-relativistic limit of the equation that we wrote before and use this fact. So I look at two components of that equation, the 0,0 component and the trace, the sum of all component, the sum of the diagonal component. So that equation was box h mu nu minus d mu d alpha h alpha nu minus d mu d alpha h alpha mu plus d mu d mu h minus eta mu nu box h minus d alpha d beta h alpha beta equals c d mu nu. And I want to look at the 0,0 component of this equation for clear reasons. I want to take the non-relativistic limit, and in the non-relativistic limit, T mu nu is dominated by the 0,0 component, which gives me just the mass density. And I want to look at the trace of this equation. Again, the trace in the non-relativistic limit is dominated by the 0,0 component. So let us take the trace of this. If I take the trace of this equation, what I get is minus twice box h minus d alpha d beta h alpha beta equals c times trace of t, which in the non-relativistic limit is minus t00. So this is non-relativistic. And of course the left hand side also simplifies in that limit. I only keep the spatial derivative. I ignore time derivative. And I'm gonna work in this particular gauge. So the 0,0 component of this equation will be Laplacian of H00 everything else on the first line is subleading, and on the second line I'm gonna have a 0, 0 means the minus eta 0, 0, which is plus Laplacian of h, and then here the leading contribution in the non-relativistic limit is di dj hij equals c t0, 0. But here we get minus 2 Laplacian h minus di dj hij is equal to minus c t0, 0. So we can combine these two equations to eliminate the trace and hij to learn that Laplacian of h0, 0 is equal to 1/2 c t0, 0, which is 1/2 c times rho. And now we can use the fact that h0, 0 is minus twice the Newtonian potential to get Laplacian of the Newtonian potential equals minus 1/4 c times rho, which tells us that c has to be minus 16 pi g. Yes.
Couldn't we just use this to identify with the Poisson equation and say that this is the Newton the potential of the identify on C over 4 with 1/16 on G without using the equation of Poisson?
No, because you would have there's still one proportionality constant, which is unknown. Right? You could. So from here, you would conclude that. What would they conclude? They would conclude that.
I want to require that when we do the Newtonian, the non-relativistic limit, we will find the Poisson equation.
Yeah. So if we want to require that, it tells us that twice h0, 0 divided by c has to be equal to Newtonian potential divided by 4 pi g. Do you agree?
Yeah, so we can fix C.
So we fix one linear combination, the ratio is 0 and c, but we wouldn't know what c is until we understand how h0, 0 is related to the Newtonian potential. Okay, so once the C is determined, we can now write the full action up to the full quadratic action for h mu nu that gives that equation of motion that we derive. The reason why I want to write the quadratic action is that first of all, we are doing field theory, so we want to know the action. But in particular, in the next lecture, we want to talk about the gravitational waves and the energy that is carried by the gravitational waves. And when we have an action, we know how to derive the energy momentum tensor and the energy flux. So that's, for instance, one usage of this, knowing the action. So I want to write an action that gives this equation of motion for h mu. So now it's actually very easy to write the action to give us a linearized equation. In general, it might not be easy. In fact, it might not even, it's generically not possible to write an action to give any equation that you write. But a linearized order is very easy. For instance, if you have a scalar field and the equation of motion for the scalar field is what is it? Box minus m squared times phi is equal to 0. Then writing an action that gives this equation is very easy. Since the equation is linear, the action that would give this equation is just up to a normalization constant, k. The action is going to be just phi times the equation of motion. And then the normalization constant, we can fix it based on other considerations. Of course, we can just change the normalization of phi so that this normalization constant is 1/2. And also we can do integration by parts to write this action in the first order form. So I do want to put one of these derivatives on phi. There will be a boundary term that usually we don't care about. And I set k to 1/2. So what we get is the usual thing. Minus 1/2 d phi squared minus minus 1/2 d phi squared plus m squared phi squared, which is what you are familiar with. Okay, now the story there is very similar. If I want to write an action that gives that equation of motion for h mu nu, the action is some normalization constant that now we can determine times h mu nu epsilon mu nu alpha beta times h alpha beta. So remember, this epsilon is that differential operator that sits there. It's the second order differential operator. So there will be a normalization constant here. Let's call it k for the moment. And then we have already decided that the way we couple h mu nu to sources is this way. So we have fixed the normalization of h mu nu. And now that we know c, this k is determined. So this k has to be, if I derive the equation of motion for h mu nu from here, what do I get? There will be twice k epsilon mu nu alpha beta h alpha beta plus 1/2 t mu nu equals 0. Twice because we have two h's here. So for these to agree with that equation, we have to identify k with for C over, sorry. So if this wants to agree, so we get minus 1 over 4k, so minus 1 over 4k has to be equal to C. So k is minus 1 over 4c. And then we can go through the exercise of doing integration by parts to write the action in the first order form, meaning that having only one derivative acting on phi. So S first order will is obtained by, let me see one for a second. First order is obtained by doing some partial integration. So if I plug that value for C in here, I get 1 over 64 pi g integral d4x. And then I will have the mu h alpha beta squared plus a bunch of other terms. And now, of course, there is a coupling with the source. So 1/2 d4x h mu nu t mu nu.
Suppose that t mu nu is 0, then it means that we have an action only for the field itself at field.
Yeah, you can have free, you can have gravitational waves in vacuum.
For the t mu nu is equal to 0.
Right, t mu nu matter is equal to 0. Yeah.
So can you say that if t mu nu is equal to 0, then this action has the symmetry under h going to minus h, but that symmetry is broken if t mu nu is not equal to 0.
Yeah, at this order, yeah, that's true.
At this order, okay.
Yeah.
That
Eventually, no, because then we are gonna add higher order terms in it.
okay. So at the lowest order it is true, but not for higher orders.
Okay, so now that we have the action, we can, yes, we can consider the vacuum solution, in which case t mu nu is equal to 0, and ask what would be the energy momentum flux. In particular, the next section we are going to be interested in transverse traceless waves, where h mu nu, for instance, we have a wave that moves along x direction, and or h mu nu has the following form. We have h y y equals minus h z z equals some h plus of t and x, and h y z is equal to h z y, obviously, equals some h cross of t and x. And for instance, with this, for this configuration, we can ask what is the energy momentum tensor, or in particular, what is the energy flux. And for this particular choice, and all other components are 0. So h mu nu equal to 0. No, other h mu nu components are 0. Right, so this is the form of the waves that, gravitational waves that we get. If you like to see it as a matrix, then this H mu nu matrix, which is gonna look like H plus minus H plus, H cross, and then 0 everywhere else.
Is there any reason for taking? Is there any reason for these conventions?
You will see in the next lecture. So we want to consider, for instance, this configuration, and ask what is the energy momentum tensor for this configuration. Now, if I consider this particular configuration, the action simplifies a lot. It actually becomes an effectively two-dimensional problem. And all those other terms will be 0 if I plug this in. I will get an action for this H plus and H cross, which is 1 over so I get a factor of 2, so I get 1 over 32 pi g times integral, a two-dimensional integral dt dx, h plus dot squared minus h plus prime squared. And then similarly for the cross term. So it becomes just like a scalar field in two dimensions for which we can derive the T mu nu. In particular, the energy flux, which is minus T01. So energy flux, which is minus T01, for this action is just 1 over 16 pi g. So this is very similar to what we did for a scalar field, right? Just this H plus and H cross that appear here, they are now they have an action which is like the action of a scalar field in two dimensions, for which we can write T mu nu. There is some overall normalization constant, so we get H plus dot squared plus H cross dot squared. Remember, the answer for a scalar field was phi dot squared with some overall normalization, 1 over 4 pi g. Now we have a different overall normalization, so we get H plus dot squared and H cross dot squared. Now in the next lecture, we will see that how we use it to calculate the energy flux or the luminosity of some source of gravitational waves.
In the equation for H, there was a term which depended on the trace of H. So that's why you took H, Y, Y, and H Z to be negative of each other, so that the trace can be 0. And the equation becomes simple.
Yeah, you can set the trace to 0 using a gauge transformation. So we are gonna talk about the gravitational waves in vacuum, and there we show that you can use a gauge in which the components of H will look like this.
By gauge you mean choice for Xi?
Yes. So this is of course something that you have to get used to using like in GR. That's one of the most common things that you do. You go to a gauge in which the calculation becomes easy. Otherwise, there are so many indices that one can hardly do calculation.
Is that easy to see that there exists a gauge in which the trace is 0, or do you have to calculate that and ask that question first? That is there a gauge in which the trace is 0, or is it immediately manifest?
Well, local you can say to 0. Sometimes there might be global issues with this kind of choices. So here, in the case of gravitational waves, we are gonna verify carefully that this is a possibility.